Okay, so remember, Thursday, last day to hand in any missed assignments. That's also the day of the diploma exam. Your diploma exam is Thursday morning, 8:30 a.m. in this room. Exam actually starts at 9, but you want to be here a little bit earlier. There'll be instructions. You need to clear calculators. So try and be a little bit early. I'm not going to look at any one in particular. Don't want to single anyone out. Try and be here early, okay? Otherwise, you'll miss the instructions. So I gave yesterday, sorry, I think it's over there, I think. Right, so yesterday I gave you guys that chapters 9 through 11 review, and I said that that's going to be collected for marks. It's going to be due tomorrow because we don't have time for an exam in this unit, so I need something to give you a mark. So I will count it as a unit exam, but only half weighting, okay? So if you weren't here yesterday, it's on that top, just beside that window there. It's sitting up there. You need to make sure you get that and be working on it because it's due tomorrow. The other thing I will do is tomorrow after school, I'll stay here till about 5 o'clock and actually do some formal review, at least for the first three chapters, Unit 1. And if I have time, we'll go into trig a little bit, okay? So that'll be tomorrow after school, starting about 3:40 or so. And then actually, let's say closer to 4 o'clock because I do have outside supervision tomorrow after school. But we'll probably about 10 to 4 or so should be able to start until about 5 o'clock or so. So we should be able to review at least the first unit and maybe do some trig stuff as well. Okay? So that'll be tomorrow after school. So the very last part of this chapter deals with binomial theorem. So we're looking at the expansion of x plus y to the power n. So n is the exponent, and what happens when n goes between 0 and 6? Well, when n is 0, anything to the power 0 is 1. Doesn't matter what that base is. X plus y to the 1 is x plus y. X plus y all squared is the trinomial that's listed there, and then you can see all the other ones are done. So you may want to do the expansions for yourself to verify the above results, but they are all correct. Now, we see some patterns forming here, and what we're working towards is a process that we can follow to take any binomial, raise it to any power. Instead of physically multiplying them all out, there are some patterns that we see here, some tricks that we can use to expand any binomial raised to any power quite quickly, instead of physically multiplying them all out. So let's observe these patterns. The first thing we should notice is that the number of terms is always one more than n. That very first row, x plus y to the power 0, has one term, the number 1. N was 0, there's one term. The next row, x plus y to the power 1, is x plus y. The exponent is 1, there are two terms. And that pattern continues. If you look at the very last row, when n is 6, if you count up all these terms, there'll be 7 terms there. So that's the first thing that we notice, is that the number of terms is always n plus 1. One more than the value of n. The second statement says the sum of the exponents of x and y in each term is what? Well, no matter which row you look at, if you add the exponents, looking at this, actually starting with the second row, The first row would be 1 times x to the 0. There's only one exponent there, and that is the 0 on the x. I mean, 1 is the same as x to the power 0. But if you skip to the next row and you add the exponents together, for each term, they're 1s, right? There's only one term there. The power on x is 1, the power on y is 1. So the degree of each term is 1, and that matches the n value. Go back to the previous one, the degree is 0, that matches the n value. If you take the next row, this x plus y squared, the degree of the first term is 2. The degree of the second term would be 1 plus 1, which is 2, and the degree of the last term is 2. Again, the degree of each term, or the sum of the exponents in each term, in every case, matches the value of n. N is the exponent. If we skip down to the last row, where n is 6, that's the degree of this term. If you add the powers on the x and the y for the next term, 5 plus 1 is 6. 4 plus 2 is 6. 3 plus 3 is 6, and so on. So in each term, when you add the powers together, it equals the value of n. So the sum of the exponents of x and y in each term is n. If you look at the pattern for the x values, and let's look at the very last row. It's the same pattern for all of them, but let's just look at the last row. Okay? The power on x, which is the first term of the binomial, is 6 for the first term. And then those powers on x, if you look, they decrease by 1 as you go term to term. So the exponents of n decrease term by term from n down to 0. So x is the first term of the binomial, right? First term of the binomial. Y, the second term in the binomial, it starts with the first term in the expansion. There is no y there, which is technically y to the power 0. And then the next term is y to the 1, y squared, y cubed, and so on. So the exponents of y increase term by term from 0 up to n. And the last sentence says the coefficients of each expansion, we say they form a symmetrical arrangement. So what does that mean, a symmetrical arrangement? Well, if we wrote just the coefficients, and I'm going to do that on the side here, the coefficients in the expansion. So the first row is just 1. Again, that's the same as 1x to the 0, coefficient of 1. The next row, the coefficients are also 1. It's 1x plus 1y. The next row, the coefficients are 1, 2, 1. The next row, the coefficients are 1, 3, 3, 1. So this is what it means by symmetrical. There are some values that repeat. In every second row, there's values that repeat. But look at any row. The first term matches the last term. The second term matches the second last term. And that pattern will continue. If we skip all the way to the last row, the coefficients are 1, 6, 15, 20, 15, 6, and 1. The first coefficient matches the last. The second matches the second last. The third matches the third last. That's what's meant by a symmetrical arrangement. And those coefficients are written down there below as well. The coefficients in the above expansion can be put in a triangular array known as Pascal's triangle. And that's named after a French mathematician who developed applications of this triangle in the 17th century. So those numbers represent the coefficients from all the expansions above. And we're going to use this Pascal's triangle. And you don't have to memorize the whole thing, because again, there is a pattern here. Each row starts with the 1 and ends with the 1. Okay? To get past the second row, again, each row starts with the 1 and ends with the 1. If you get to the third row, starts with the 1, ends with the 1. You can get this 2 by adding the two numbers directly above together. 1 plus 1 will give you the 2. Each row starts with the 1, ends with the 1. So the fourth row starts with the 1, ends with the 1. This 3 is found by adding the two numbers above it together. 1 plus 2 gives you 3. And then 2 plus 1 also gives you 3. The next row, which will be the fifth row, 1, 2, 3, 4, 5, starts with the 1, ends with the 1. The 4 can be gotten by adding the 1 and 3 together. The 6 can be gotten by adding the 3 and the 3 together. The 4 can be gotten by adding the 3 and the 1 together directly above. So that's how we can generate Pascal's triangle, this triangular array of numbers. So that's one way to do it. Another way is by using combinations. You can also do it using combinations. That very number 1 at the top could be found by going 0C0. Then the next row, the two ones, are 1C0 and 1C1. The next row, 1, 2, 1, can be found by using combinations. 2C0, 2C1, and 2C2, and so on. So you can also get those numbers by using combinations. And we're going to see there's sometimes where we'll generate Pascal's triangle to get our coefficients. And there's going to be other examples, other cases when we're going to use combinations. So in this lesson, you may be asked to expand a binomial or simply find a term in the expansion. The above warm-up leads to the general formula for binomial expansion known as the binomial theorem. So basically what it says, binomial theorem says that x plus y to the n, so that's the expansion. And as I said, the coefficients can be found by using combinations. And so the first coefficient can be found by NC0. N corresponds to the power on x plus y. And each term, notice what's happening to the r value, it's increasing by 1. You're going from NC0 to NC1 to NC2, all the way down to the final term, which will be NCN, will be the last term. And the first term in the binomial, you're expanding x plus y, is x to the n. And then as we saw earlier, the powers on x decrease by 1 as you go term to term. The second term in the expansion, which is y, starts at y to the 0, and then the powers increase by 1 as you go term to term. And this leads to the general term of the expansion, and this formula is on the formula sheet. The general term is nck, x to the n minus k, y to the k. This is on the formula sheet, but it says it is the k plus first term in the expansion. All right, so the k value, notice it says t sub k plus 1. The k value appears there in the formula, there in the formula, and there in the formula. So you need to know what the k value is. As it says, this will give you the t sub k plus 1, or the k plus first term. So what that means is that, let's say you wanted to find the third term in an expansion. Using this formula, if you wanted to find t sub 3, that would be t sub 2 plus 1, because the general formula involves t sub k plus 1. So to get t sub 3, k would have to be 2. So we're going to see that the value of k is 1 less than the term number. That's what you need to remember. And it comes from this general term formula. The value of k is 1 less than the term number. And that's what it says there below. So again, this formula is on the formula sheet. You might see a question where it asks you to do an entire expansion, and we'll do examples like that. Or you might be asked to find just a specific term. And it's much quicker to use the general term formula than to do the entire expansion and then go back. Like for this question, what is the third term in this expansion? Well, we're going to use the general term formula. T sub k plus 1 will equal nck x to the n minus k, y to the power k. We want to find the third term. We want to find t sub 3. So in that case, k would have to be 2. So that when you let k equal 2, you'll get 2 plus 1, which is 3. Remember, k is always 1 less than the term number. So the value of n is 7. It's going to be 7c2. The value of k is 2. X refers to the first term in the expansion, which is x in this case, to the power n minus k. Y refers to the second term in the binomial, which in this case is y, and that is raised to the power k. So we can go to our calculator and find out what 7c2 is. Seven C2 is 21. X to the fifth y squared. That would be the third term in this expansion. On to the next question. What is the middle term in that expansion? So to do this, you have to remember that the number of terms is always one more than n. The number of terms is n plus 1, which in this case would be 9. There are 9 terms in this entire expansion. So the middle term would be the fifth term, because you'd have 4 on either side. The middle term would equal the fifth term, because again, you'd have 4 on either side. And so our k value is 4. Remember, the k value is always 1 less than the term number. So in the expansion, it'll be term 5 will equal, as we said, it'll be t sub 4 plus 1, because that's a general term formula. Again, this is another reason why the value of k would have to be 4. And that equals nck. So n, the power on the expansion is 8. C, we said k was 4. Again, x refers to the first term in the binomial. In this case, we're expanding 2x minus 3. So when we use the general term formula, x refers to the first term of the binomial, which is 2x to the n minus k. And y refers to the second term of the binomial, which in this case is negative 3, which is raised to the power k. So using the general term formula, that's what it's going to look like. 8c4 8c4 is 70. And then you're going to have 2x all to the power 4, which will be 16x to the fourth. And negative 3 to the power 4 is positive 81. So your coefficient would be found by multiplying 70, 16, and 81. Which is 90,720. X to the fourth. So that would be the middle term in that expansion. So we found the original coefficient, the HC4, by using combinations, obviously. If we use Pascal's triangle, you'd get the 70 that way as well. Right? You'd have to go all the way down to the 9th row and generate Pascal's triangle, and we will do some of that, like when we get down to example 4. But you'd have to get down to the 9th row, and then the middle term, the 5th term, you'd see the number 70 there, which is then multiplied by the 16 and the 81 to get your final coefficient. Example 3, find the 4th term in the expansion. So t sub 4 would be t sub 3 plus 1. Again, this tells you the value of k. The value of k is always 1 less than the term number. So we could have got the value of k by, again, remembering that k is always 1 less than the term number. So if you want the 4th term, k would be 3. So using the term, or the general term formula, it would be n c k 6c3. And again, when we say x, we're referring to the first term of the binomial, which in this case is 1 over x, which we will write as x to the negative 1, to the n minus k. Y refers to the second term of the binomial, which is x squared, and that's raised to the power k. So 631, or 6c3, I should say, is 20 x to the negative 3, because 6 take away 3 is 3, but then you got to multiply that by the negative 1, times x to the 6. And now we can simplify it by combining those x terms together by adding the exponents. And our final answer is 20x cubed. That is the fourth term in that expansion. If you wanted to, I mean, you could do the expansion from start to finish and then go back and count the fourth term. But using the general term formula is usually quicker and easier. Usually. Number 4, though, asks us to do the entire expansion. So to do that, we're going to use Pascal's triangle and the pattern that we saw at the very start. So I'm going to start by generating Pascal's triangle here on the right. Each row starts with a 1 and ends with a 1. To get the number above, you add the two numbers together. Each row starts with a 1, ends with a 1. To get the number above, add the numbers together. So I'm going to go a little further than I need to here, and then we'll talk about how you know what the appropriate row would be. We want to expand 3x take away 4 to the power 3. We said at the start that the number of terms is always 1 more than n. That means there has to be 4 terms. So we want the row that has 4 numbers in it. So it has to be that row right there. Also, the other reason that we know that that is the appropriate row is that the second number matches n. Right? N is 3, it's power 3. That matches the second number. If we were using the next row, that would be when n is 4. That's the second number, and so on. So these are our coefficients. We'll write those down first. And now, we'll use that pattern that we talked about on the first page. The first term in the binomial is 3x. The first term in the expansion starts with 3x to the power 3, and then the powers on 3x decrease by 1 as you go term to term. The second term in the binomial is negative 4. That starts at power 0, and those powers increase by 1 as we go term to term. And notice that for now, I'm putting plus signs in between each term. They're not all going to stay positive. We'll see as we simplify this, some of these terms are going to become negative. So the first term is 1 times 3x all cubed times negative 1 to the 0, which is 1. Anything to the 0 is 1. So read it's just 3x all cubed. That's 27x cubed. Plus. For this next term, it'll be 3 times 3x all squared, which is 9x squared, times negative 4. Plus. 3 times 3x is 9x times negative 4 all squared, which is positive 16. Plus 1 times 1, because 3x all to the 0 is 1, times negative 4 all cubed is negative 64. So we are left with 27x cubed. 3 times 9 is 27, times negative 4 is negative 108. x squared. 9 times 16 is positive 144x minus 64. So there's your expansion. Probably a little quicker than multiplying 3x minus 4 by itself 3 times. And that maybe is debatable. Maybe it would be quicker to multiply 3x minus 4 by itself 3 times. But as n gets larger, it is definitely quicker to use this method, this pattern, in order to do your expansion. Number 5, one term in the expansion of x plus a to the 10th is given. Determine the numerical value of a. So using the general term formula, which again is nck, x to the n minus k, y to the k, we know that n is 10. That is the exponent on x plus a. We need to figure out what our k value is. Again, x refers to the first term in the binomial, which is x in this case, to the 10 minus k. Y refers to the second term of the binomial, which in this case is a, that needs to be raised to the value or power of k. And this must equal 3,281,250 x to the fourth. If we compare these two, the only place that we see the x is there and there. The power on x must, at the end, be 4. So that tells us that k has to be 6. Because the power on x, 10 minus k, in order to make that exponent on x be 4, you need k to be 6. 10 minus 6 will give you the 4. So k equals 6, and now we can write 10c6, x to the 10 minus 6, a to the power 6 equals 3,281,250 x to the fourth. We can find out what 10c6 is. C6 is 210. X to the fourth, a to the sixth equals 3,281,250 x to the fourth. So you can divide both sides by 210. Actually, let's divide both sides by 210 x to the fourth. The x to the fourth will cancel on the left, and the 210s will cancel. So we're just left with a to the sixth on the left, equaling 3,281,250 divided by 210. So a to the sixth will equal 15,625. The x to the fourth will cancel on the right as well. And so now a will be found by taking the sixth root of 15,625. The sixth root. And so our answer is 5. So there's the missing value, positive 5. Number 6, one term in the expansion is 216x squared y squared. Find the value of b. We look at the binomial that's expanded, or raised to the power 4. B is the coefficient of the y term. So we do know that n is 4. So if I'm using the general term formula, it'll be 4cn. The first term of the binomial 3x. I'm sorry. I should have put a k there, not an n. Let me fix that. 4ck. The first term of the binomial 3x is raised to the n minus k. And the second term, by, is raised to the power k. And that must equal 216x squared y squared. There's a couple different ways we can get the value of k here. Probably the easiest way is just comparing the powers on y, the letter y. Right? Our term must have the y term squared, or the y factor squared. The only place we see y is right there, and again, the y value must be squared, so k has to equal 2. So now we can say it's 4c2, 3x to the 4 minus 2. This will give us an x squared term, which we need, right? Our term is 216x squared y squared. So I need to solve for b. I need to solve for b. So 4c2 is 6. That next factor will be 3x all squared times b squared y squared equals 216x squared y squared. When we square the 3x, that gives us 9x squared. And now I can divide both sides by, well, actually, before we do that, let's multiply out that left side. 9 times 6 is 54. X squared, b squared, y squared equals 216 x squared, y squared. And now I will divide both sides by 54 x squared, y squared. 54 x squared, y squared. So that'll leave us with b squared on the left side, and on the right side, the x squareds cancel, the y squareds cancel. We're just left with 216 divided by 54. B squared is 4, so b would equal, and actually it could be plus or minus 2, because when you take the square root, the even root of 4, it's possible for it to either be, this one says b is greater than 0, right there. So it's only the positive one. B would equal 2. Okay? So that's binomial expansion. We'll do some more questions with this tomorrow. If you want to do some extra practice, you can try those questions. Page 542 to 543, 4, 6, 7, 17, D, 18, and 20. But I would probably recommend that you work on that review assignment that I gave you yesterday. It's due tomorrow, and this is where your mark's going to come. It's going to count as half of a unit exam. So definitely a chance to boost your mark. Okay, if you put the effort into it. But if you have some time, you want to do some of these questions, I will post those solutions to Google Classroom so you can check your answers. Remember tomorrow at the start of lunch, if you want to do the rewrite for exponents and logarithms, that's when it has to be. That's the only time. And then tomorrow after school, I'll spend an hour and a bit here, at least reviewing Unit 1 for those people that can make it. I will record it. I will live stream and post the video on the Google Classroom, so if you can't make it, you can still watch it. Right? But your diploma exam is Thursday morning, 8:30 a.m. here as well. Thursday is the last day to hand in any missed assignments. Okay? Go ahead. Yeah.